everyone. Happy Monday. Let's just give everyone a few more minutes to join and then we'll go ahead and get started. Thanks. Okay, we'll go ahead and cut the music. Good afternoon, everybody. Welcome to Data Engineering's Lunch number 70. I'll be your host this afternoon. My name's Akwi Ohiri. This afternoon, we'll have our speaker today will be Alex Merced, a developer and advocate at Dremio. Today, he'll be discussing Apache Iceberg, an architectural look under the covers. The co-organizers for this event are Rahul Singh and Arpan Patel. We are looking for speakers and sponsors for this event, so if you're interested in either of these opportunities, please reach out to Arpan at the email address listed below. Data community, we are part of a larger community called Data Community DC, which believes in building an inclusive environment, so no matter your race, gender, or sexual orientation, everyone is welcome, and we expect the, pardon me, and we expect respect to be given to all. Data Community DC is actually made up of a larger, pardon me. Data Community DC is actually made up of a lot of different groups, generally all focused around data. And you can find out more about all the various different groups and events at datacommunitydc.org. At DEL, we cover everything from the ingress and egress of data and everything in between. We cover everything from databases, ETL, data wrangling, and all tools and processes in the data engineering world. So I guess you could say data engineering is part of our way of life. At this point in the presentation, I'd like to invite first-timers to introduce themselves, perhaps what you work on, what your role is, and what you're looking to learn from these data engineering lunches. Please just leave that as a comment below. Group rules for this event: if you have a question, ask it. I like to defer to the presenter on when they like their questions asked. Some presenters prefer the questions at the beginning or at the break in the presentation. Other presenters just like the questions asked throughout the presentation. Please be respectful of your presenters' wishes. Also, be polite and courteous to others. And of course, please share what you know with us. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. DataStax is a partner and sponsor for our DEL lunches. Obviously, we'd like to thank them for the continued support. GW University is also a sponsor that helps provide venue space when we do have in-person events, so we'd like to thank them as well. We also have institutional and organizational sponsors listed below that we'd like to thank as well. If anyone has any job offers or is looking for a job, please drop your links in the comments below. Additionally, if anyone has any meetups, hackathons, classes, or conferences that they would like to promote, feel free to drop links to those as well. Here at Anant, we are hiring full-time and part-time platform operators, engineers, and architects. For more information, please visit our site listed below. Also, please visit our events page for more information on our upcoming events and our recurring events as well. Pardon me. I also like to promote our current Apache Cassandra runbook, runbook 5, which is focusing on JVM repair and hints and errors. Please download this latest edition before the release of our next edition. And with that, I would like to turn it over to our speaker for today, Alex. Alex, over to you. Hey, Alex, so before you go any further, I just want you to check your mic. I don't think I could hear you correctly. Still not coming through, Alex. There you go. It is a bit muffled, but I can hear you
now. Is that better? Is that a better mic?
Much better, much better. Please go ahead.
Okay, cool. We'll go with that. Cool. Okay, so let me just cue that back up. Where did it go? I accidentally closed the window with the slide deck. So let's get that back up and we will be off to the races, everybody. Good times. Okay, now let me share my screen. Let's hit slideshow and here we go. My name is Alex Merced. I'm a developer advocate here at Dremio. I definitely encourage you all to follow me on Twitter to hear about future table format related content that I'll be putting out. And that's at AM Data Lakehouse. But today's topic is going to be about Apache Iceberg. And the question becomes, what is a table format? Because that's what Apache Iceberg is. Why do we need a new one? I mean, wasn't there something like a Hive tables? What's wrong with Hive tables? Why should we switch over to Apache Iceberg? How do Apache Icebergs work? What is their architecture? What is their design? And why is that design so important? Because it's the design of how we organize like metadata and our data files that really make Apache Iceberg a very compelling next step in really doing more robust workloads on the data lake. And what happens under the covers? Like what's happening in Apache Iceberg when I insert data, when I create a table, when I update records, when I delete records, what's kind of going on there and why, like what are the benefits? Because there's actually a tremendous amount of new features that using Apache Iceberg as your table format on your data lake unlocks. Things that before were only accessible to you maybe in a data warehouse, on the OLAP side, or in traditional databases on the OLTP side. But now you can now have these features on your data lake, unlocking that sort of data lakehouse stream, that idea of having those data warehouse features on your data lake where you can have a lower cost, higher scale, more robust access to data. So first off, like what is a table format? Because we all know like what a table is. Like you've probably used a database or a data warehouse and you have your tables, you run your SQL queries on them. And generally when you're using those, you just take them for granted because the software, that database software, that data warehouse software, they abstract all of that from you. So basically, how is what is the physical files that make up my data? Doesn't matter. All I know is that I have a table that I can run analytics with. But when we get to our data lake, we're talking about sort of saving a bunch of data on object storage, something like an S3 or an Azure or Google Cloud. We may have thousands and thousands of files, Parquet files, ORC files, Avro files. And many of those files may make up one singular data set. And we want to run analytical operations on that singular data set. So we need to come up with some sort of abstraction so that way our tools, our data processing tools, can sit there and look at 1,000 files and treat them as one data set, as one table. And that's the purpose of a table format. It basically creates sort of that mechanism so that way any kind of data processing engine can look at a huge amount of files and say, that's one table. Now, the original solution to this was done through Hive. Okay, so basically what happened is that once upon a time, instead of object storage, we'd be using like a Hadoop cluster, and you'd be writing analytical jobs through MapReduce, which wasn't always the most fun thing to do in the world. So then they developed Hive, and Hive will allow you to write SQL statements and then convert those into MapReduce jobs and make life a lot easier. But in order to write those SQL statements, or in order to write those jobs, we had to understand, like, what is the table that you're referring to? So Hive had to come up with some sort of way to determine what is the table. And the approach that they took was to say, hey, any files in a particular directory is the table. Okay, it doesn't matter what type of files are. If it's in this table, if it's in this folder, it's part of the table. So for our table 1, all the files inside of the table 1 directory would be part of table 1. And that was the definition. So if it's in the folder, it's part of the table. If it's not in the folder, it isn't. Which worked. Like that's simple enough, and it works. And that became kind of the standard way of doing things. And then you would have like partitioning, where you have like subfolders, and we develop the data in that folder into subfolders, and so forth and so forth. And there was a lot of pros to this. It works because it became the de facto standard. It pretty much works with every processing engine. So any engine that runs analytics on your data lake data, chances are at least works with Hive. Okay, so you have that ubiquity when you're using Hive tables. It has more, you can have more efficient access patterns, because not only can you define a table, but you can do things like partitioning that allows you to kind of define those like subsections of a table, so you can run faster queries when you're querying only like that subdivision of your data. It was file format agnostic. You can mix all sorts of different types of files in that folder, but everything in that folder would still be treated as one table, one singular table that you'd be running operations on. And because of the way it was organized, you could atomically update a whole partition. It would just essentially, like, you say, hey, I want to update every record in this, or delete this whole partition. You could do that pretty efficiently at the partition level, because basically, like, okay, hey, this data is in this partition, and now I'm going to go edit that data. And it provided us a single central answer to what is a table. So going forward, you're not having to do this painstaking saying, okay, hey, these 1,000 files are my data set, and have to do that manually, which could lead to all sorts of problems, because different teams running analytics in the same data set, they may accidentally exclude a file or accidentally add a file. You run into this inconsistency problem. But with Hive, the table's whatever is in the folder. And now everyone's running the operations on the same data, clearly defined. So that was like the real like juice to this whole table format business. But it wasn't perfect. There were definitely cons. Smaller updates were really inefficient because of the way it worked. You could do a partition level update because it's going to essentially rewrite that partition, or go through that partition's worth of records. Now imagine you want to delete just one record. Okay, I want to delete one record. It may be in a partition, but now it still has to scan through like that entire partition to find that one record to mark it as deleted and write some files. It becomes really costly to run those really small updates or small deletes based on its current design, the sort of directory-based design. When you start wanting to change multiple partitions, it becomes harder to do that safely with just like your pure Hive format. And in practice, sometimes you'd have difficulty running multiple jobs on the same data set safely. Okay, so there's all this issue like safety, meaning, well, basically if we're adding multiple partitions or running multiple jobs on the same data, what can happen is that maybe one finishes first before the other, or something happens in between, and you end up having inconsistency in the data that can affect the people who are querying the data. Now they're querying imperfect data, which leads to imperfect insights. And well, we want to avoid that. Okay. And then because you're just listing every file in a directory, like when you're running a query, I may be able to narrow down to a partition, but I'm still having to go iterate through like every file in that partition. And that's a lot of, IO action, a lot of opening of the file, reading of the file, closing of the file, which can be very time consuming when you're processing that query. Now, particularly when it came to like partitioning, well, the way you would partition is you would say, hey, this partition my table by this column. So let's say I want to partition my table by month. Okay, the problem is there isn't really a month field. There's a timestamp field. I have a timestamp for when my records were created or for when a sale was made. So what I'd have to do is take that timestamp field and use that to make a month column to track the month, and then I can partition by month. Problem is, Hive doesn't implicitly know that this field, this month field, is related to that timestamp field. So what happened is that for me to take advantage of the partitioning, I have to, when I put in my filter, I can't just say only records within this timestamp. I have to say within this timestamp and on this month. So you end up having these like longer queries that are not necessarily intuitive. So if you're a data consumer, data analyst, data scientist, someone who's querying the data, and you're not aware of specifically how the data is partitioned, you might forget to include that, for this month part of the query. And what's going to happen is you end up doing a full table scan. And so you'd end up having a lot of these accidental full table scans, which could take a lot longer because you're scanning all the data instead of just a subsection of the data. So basically, yes, you had partitioning, but it wasn't necessarily as intuitive as it could be. And if you want to keep track of stats in the table, you would have to run these like explain queries to collect the stats on the table. And these basically you have to go back, and that would have to go read all the files to collect all these statistics. So you often had stale statistics in between these jobs, and then these jobs were oftentimes like they would take a long time. So these are all kind of issues that were with the Hive table format. So the inability to kind of do certain things, certain like updates and deletes safely, the ability to make it kind of intuitive so we can avoid those full table scans, and making sure we always have up-to-date statistics. So clearly there is a need to solve these problems. So there was a need for a new table format. And then at Netflix, because Netflix was running into a lot of these issues and they wanted to kind of fix these issues, they began work on trying to find a better way to track the tables on their data lake. Okay. They were worried about correctness, consistency, like does the table working? Having faster query planning and execution. Okay, so whether it's a small operation or a large operation, if we can speed that process up, which can be done by scanning less files, running less input, open file, close file, like really limiting like the amount of files we have to work with per query, we can really like speed that process up. Allow users not to have to worry about the physical layout of the data. Okay, so in this case, not have to worry about whether files are in the right folder, and have to worry about like how is a partition. Like, long as if I query that timestamp field, I should be able to benefit from the timestamp and benefit from the partitioning underneath the table. I should be able to update the table. I should be able to change the schema, change how the table is partitioned, and so forth. Versus having to rewrite the table every time I want to do that, because that can be really expensive to rewrite terabytes of data every time you want to change the partition, anytime you want to change the schema, and so forth. So we want to have that kind of flexibility. And we want to be able to do this all at like terabyte, petabyte scale, okay? We want to be able to do this faster, better. So they came up with a different approach. And this approach was, instead of saying, the table is all the files in a particular folder, instead we'll actually have a list of files. So it doesn't matter where the file's physically located. We know exactly what files make up this particular table because they're explicitly listed out. And basically there's a little bit more to it as far as like having different layers of metadata that allow you to track that. But basically, that's sort of the fundamental difference. By being a little bit more granular in how you define the table, it's going to give us more flexibility to actually do things faster. And this is what became known as Iceberg. Now, what is Iceberg and what isn't Iceberg? Iceberg is a table format specification. It's a standard of how a table and the metadata around that table should be tracked. Okay, we'll go over that architecture of that standard. Okay, and not only do you have this sort of specification for what the table should look like and what should be included in the metadata, there are a set of libraries and APIs that basically anyone who's looking to incorporate Iceberg into their tools, they can use to help. Okay, so like a lot of different like Spark extensions, a Java API, a Python API, all these different tools that help you work with Iceberg tables that match that specification. But what Iceberg isn't, it's not a storage engine. Okay, so you'd still have to store your data somewhere. So it could be like an S3, Azure, HDFS, however you want to store your data. So the actual files are still have to be stored somewhere. It's not an execution engine. It's not Iceberg that's running the queries. It's the particular engine that you want to use, which could be like a Spark or a Dremio. And again, each engine is up to them to sort of implement the ability to like read these standards and use these features and so forth. Again, that's there's a difference in the engine. The Iceberg is just the standard of what the table is. It's not a service. Okay, so it's not this running process that's going to maintain these tables. It's just the specification, and then the tools you'll use will then embrace that specification. And the beauty of that is you end up having a variety of tools that are open to you because it's an open format. And with that open specification, anyone can, so you can have one Iceberg table and multiple tools can then do reads and writes to it. And you can use whatever is like the best tool available at the time. You're not like locked in anywhere. Okay, and again, that whole data lakehouse stream. Okay, so now I'll start getting into like the architecture of an Apache Iceberg table. So essentially what's going to happen is that you have sort of three sort of main layers. Okay, you have the catalog, the metadata layer with all the different types of metadata, and then you actually have the data layer, which is the actual data files. Okay, and we're going to kind of go through each one. So first off, you generally have the catalog. Now, the way to think of a catalog in this regard is that I think of it like a phone book. Okay, so basically, if I wanted to know back in the 90s, like, what was Bob's phone number, I'd go grab my phone book. Okay, I probably should, use like Google as the analogy nowadays, but we'll use phone book. I'll go look at Bob's number, and there's Bob's number. Okay, same thing with the Iceberg catalog. It tracks what is the newest metadata file for a particular table. So if I'm saying, hey, I'm looking for table 1, it's the catalog that the engine goes to sit there and say, hey, where is the metadata for table 1? And the Iceberg catalog will point to it. Now, the reason why the Iceberg catalog is extra important is because it's used to kind of make sure that changes are atomic, so that you can have asset guarantees when working with these tables on your data lake. So generally, that pointer, that catalog is going to be something that has some sort of atomic guarantee. So this could be like a Hive metastore. This could be AWS Glue. It could be, you could actually use like relational databases, anything that supports JDBC. Now they're just adding like a REST catalog where you can have like a standard API design. There's a thing called Project Nessie that's actually designed for this purpose that actually adds all sorts of extra features to Iceberg. So you can have like branching and very like GitHub-like features with your Iceberg tables. So that's another thing you can use as a catalog. But the main function is that it's going to list all your tables and then point to where that newest metadata file is. Okay. So basically, whenever like an engine is looking for a table, that's going to be their first stop. Like, where is this table exist? Okay. So the actual metadata of the table are just files that are wherever you're storing your data. And it always starts with the metadata file. Think of the metadata file as the table-wide metadata. It's like the global metadata that defines the table. So it's going to have something like a unique table ID, the physical location to where this table's default directory is. All the files don't have to be in that directory, but when it like writes files, it'll generally by default write it to that default location. It's going to have its current schema, and actually will have a historical list of all previous schemas. It'll have its current partitioning specification and any previous partitioning specification, the current snapshot and the list of any previous snapshots. So basically all the data that an engine would need to understand the table as a whole is in this file. Okay, and at this point, the engine has to decide, like, well, am I looking at the data now or in the past? And that's where these snapshots come in. So we're going to assume that, hey, I just want to look at the data as it is. So I would want to look at the current snapshot. So this current snapshot ID would tell me, hey, what is the newest snapshot and what is the manifest list that has the details for that snapshot? Okay, and that's going to take us to the manifest list. So we looked at the table as a whole. Now we're looking at the specific state or the particular moment in time we're looking at that table at. And what a manifest list is, it's going to list not files. They're going to have a list of other special files called manifests. Because the idea is, instead of just like listing each file individually and having this big long list of files, let's break them up into groups, typically like by your partitioning needs. So if you partition the table, what's going to happen is you're going to have all these groups of files called manifest files. And then this manifest list is going to list all the manifest files. So I'm basically, instead of taking a look at the list of files, I'm taking a look at the list of files. But the beauty of that is because I have all these manifests broken up by like partitioning and other factors, at this point, the engine can take a look at the partitioning specification of each of these manifests and say, hey, do I need to scan this? So instead of having to go through file by file to determine whether I need to scan it, I can eliminate groups of files from my query planning in one fell swoop, which really speeds up the planning process. So once we eliminate all these manifests that we don't need to look at, and we figure out which ones we do need to look at, we'll then move on to those manifests. And then those manifests will list the individual files and actually have data on like what are the values in the columns, what partition are they in, and we can do further pruning here, like minimum, maximum pruning. So for example, if I'm querying for anybody who's above the age of 20, then what's going to happen is that each of those manifests will list, hey, for the age column, for this file, what is the range? Like what is the highest value we have for age? What is the lowest value for age in this particular file? And I can determine which files are worth looking at. So now we can eliminate more files. And at this point, we haven't opened up any files. Okay, all we've opened up is these few metadata files. So the amount of those file open, file close operations have really shrank. And we've also reduced the number of files we're eventually going to scan because we have this extra data to allow us to plan that query faster. So that's like the benefit that Iceberg provides tools that embrace it. It's providing all this data that allows them to make these really, really efficient query plans, which result in really, really efficient scans of the data. Okay, and then again, once we have narrowed down which the manifest files, and we've gone there and then narrowed down which files we want to look at, we'll then scan the files we've determined we need to look at. And then you get a nice, quick executed query. So let's like see that in action. Okay, so we'll do a couple of different like queries and just kind of see like that step-by-step process. So first thing we're going to do is we're going to create a table. Okay, so standard like create table statement in SQL. So we define some fields. Now this is assuming Spark. So this is assuming like Spark extension. So in Spark, you'd actually have to like explicitly say like using Iceberg. That will tell it to like use the Iceberg extensions when creating this table. Then partition by. Now notice this. Notice how I say hour, kind of like this function called hour, and then I specify the field or the timestamp field for order. This is a cool feature in Iceberg. What it allows you to do is you have these partitioning transforms for defining how you partition your table. So instead of me having to make that separate month field and having to make sure that all my consumers know to query that month field, I tell it to query by, in this case, hour. So it'll separate all the data by hour. But when my consumers query the data, it knows, because of the way we defined it, it knows that the way we partitioned it is related to this field. So when this field is filtered, if I say, hey, get me all data between June 30th, 2020 to June 30th, 2022, it'll know, since I'm using the timestamp field, that it can take advantage of the partitioning. So the people who are actually querying the table don't need to understand the partitioning to get advantage of it. If they query the right fields, they're just going to get a faster query. And that makes it easier to benefit from this design. So that's a really cool feature. It's referred to as hidden partitioning. I did publish an article specifically on that feature. Oh, let me go back. Oh, nope, it disappeared. So let me go back to that slide. That's where I was. Thank you. Okay, so we're creating the table. Now what's going to happen when we create the table? The first thing that's going to happen is that there's no table that exists. So what's going to happen is that there's no data being added to it yet. So no data files have to be created. And since there's no data files, there's no manifest files that are needed because we don't need to track any groups of files. And since there's no data, there's no snapshot. So there's no manifest. So the only thing that needs to be created is a metadata file that, again, has the definition of the table. And then we need to track where that metadata file is in the catalogs, again, which could be Hive Metastore, AWS Glue, Nessie, any of these choices. So if we take a look at here, like this is basically, imagine like this is the folder where the default location for this table. In that folder, it's going to create a metadata folder and a data folder. And right now, we just have this metadata.json. And you'll see that every time we make a change to the table, it's going to create a new metadata.json, and it's going to keep incrementing the version numbers. So it'll be v1, v2, v3, v4. And it's going to be using that number to help sort of like make sure that everything is lined up. Okay, now let's actually put data in this table we just created. So if I insert into the table these following values, what's going to happen is that first thing it's going to do is going to write the data file. So it's going to say, okay, hey, this is the data that I'm writing based on the partitioning. So based on however the table is partitioned, it'll group any data being added and then write the corresponding data files. And then it'll make a manifest file generally for each partition, saying, okay, these are all the files that relate to data in this partition. And then the manifest list will be written that lists all the manifest files that belong to this particular snapshot. And then a new metadata.json gets written that says, okay, here's the table. This is like the definition of the table. And here are the snapshots, which we have two now. We have the snapshot we just created because we just changed the table. But technically, that moment we created the table was a separate snapshot that exists. So snapshot 0. And then the metadata file knows each one. And then we update the catalog. So that way the catalog points to v2 metadata, not to the v1 metadata. Okay, you can see that all here in the actual physical files. See a new v2 gets created. There's a snapshot, there's an Avro file, and then here's like the manifest file I got created. And then the data file just got saved as a Parquet file by default. Although you can do ORC and Avro as well. Okay. So there we inserted data. Now let's see what happens, okay, when we do an upsert. So what we're going to do is that we have our table, table 1. And what we want to do is take all this data from our staging table here, and we're going to merge them together. So we're going to say, okay, merge these two tables based on where the order ID in table 1 matches the order ID in the staging table. If they match, then update them. Say, okay, let's update this particular property. If they don't match, well, then that's a record we don't have yet, so insert that into the table. Okay, and so it's going to run this operation. Okay, the query will get planned. And basically what's going to happen is that it's going to write the data files. So all the new records get written into different data files based on their partitioning. So again, by hour. So we're seeing like, hey, look, there's different hours now that each get their own folder. And then we're going to have multiple manifest files that'll list the different data files, again, based on partition. And then we're going to have our snapshot, the manifest list, that's going to list all the manifests that belong to that snapshot. And then we create a new metadata, v3.metadata, that's going to track the newest snapshot plus the previous two snapshots. And the cool thing is, in the future, when I query, I can specify which snapshot I'm querying. This is the feature called time travel. So I'm going to be able to say, hey, I want to query snapshot 1. I want to query snapshot 0. And it'll query the data as it was at that snapshot. So I have that ability to go back in time, which is really cool. Also, I can also roll back changes and basically makes it a little less painful to make a mistake because you're not rewriting all your data because you made a mistake. Okay. So now that we've done that, let's actually query the data that we have. So if I just run a select on the table, okay, what's going to happen is that the engine is first going to go over to the catalog, say, hey, I want to scan table 1, which the catalog is going to point it over to the metadata file, in this case, the newest one, which is v3. And that's going to take a look at this. And since we specified nothing like about time travel or a particular timestamp, we're just going to go to the newest snapshot. So I'm going to go to the newest snapshot. The newest snapshot says, hey, this is the details. These are the manifests for the snapshot. We then take a look at the manifest and look at the files, get the list of files for that snapshot, and we scan them. And then there you go. You've scanned the table. Okay. So basically, pretty straightforward. When it reads, it just goes through that process of catalog, metadata, manifest list, manifest file. Then it gets a list of files to actually scan. So that works pretty straightforward. Now, what happens if I want to scan data based on a particular field? So in this case, we're using the timestamp field. So I'm going to filter and say, hey, I only want data that was on January 26, 2021. Now, remember, we did partition based on the timestamp field. Okay. So even though it's partitioned by hour, it is aware that, hey, technically, this is the field you use for partitioning. So even though they didn't specify a particular hour that they wanted, they're still going to get the benefit. Okay, so what's going to happen is that it's going to go to the catalog. The catalog's going to point it to the metadata file. It's going to get the newest snapshot, the manifest list. But the manifest list is going to break down the different manifests. So in this case, we have like 2 manifests by partition. So we're going to say, okay, hey, there's these two partitions. And then so it's going to go to the manifest file, eliminate the ones that don't apply to this particular query. And instead of scanning all the data files, it's only going to scan the ones that apply based on the partitioning. So basically that query is now going to be a lot faster because you're scanning less files. Again, less having to open files, read files, close files. And again, the more of that you do, the longer it's going to take to query. Because essentially there's only really 2 ways to speed up a query. Do less things or do those things faster with faster computing power. Okay, either way, you'll speed up, but more computing power is more expensive. So if we can reduce the amount of work it has to do to get from point A to point Z, not only do you get there faster, but you get there cheaper, and you're saving money on your cloud bill at the end of the month. Okay. Now, here we're going to select all, but now notice this time we're doing as of. That means you're specifying that you want time travel. You're saying, hey, I want to scan the table as of this date. Okay. So now what's going to happen is that it's going to scan the catalog, go to the metadata file, and then it's going to take a look for the snapshot, the newest snapshot that's on or prior to this timestamp, which is going to be snapshot 1. So it's going to use snapshot 1 to scan the table. So instead of going this path, it's going to go down this path and use the older manifest list, which will let it scan the older manifest file to scan the data files that represented the data at that previous point in time. So yes, you're never technically files are never being deleted in this process. You're always just adding files to represent the new state of the table, and all the old files from previous states still exist. Okay, so there are like, this is going to go for like all table formats where you're going to have to do maintenance of the table over time to make sure you don't have like too many files, but usually not a particularly tricky thing to do. But just to kind of really see the benefit of this, like this is going to be really stark. This because again, this was developed in Netflix, and Netflix had this Atlas system, where it basically gathered telemetry data, and just to kind of give you an idea of the amount of data that was being generated by this system, in 1 month, it would generate 2.7 million files in 2,688 partitions. Okay, so the problem is with so much data that using traditional processing methods, using like Hive tables, they could not process more than a few days of data at a time. Like if you need to go back more than a couple of days or look at more than a couple of days of data at a time, the queries would just take too long. Okay, and here's just like a sample like query, like the kind of queries that they would be running on that Atlas system. but more importantly is the time that it took for those queries to happen. So let's take a look. When we're taking a look at a Hive table using Parquet filters, so there is some narrowing down of things. So basically, even though you're still using a Hive table and you're kind of going through each file, you can take a look at those Parquet footers in Parquet files to kind of help narrow down, like, hey, do I need to look at this row group, this row group, this row group, which does save you some time, but you're still opening up all the files. Okay, and essentially what happened is that when you did it through this approach, basically you had 400,000 splits per day's worth of data, not combined. So it's not like total 400,000 splits. It's for each day of data you were looking at. Essentially, you had like 400,000 splits, 400,000 chunks that would require scanning. Okay, so just to run an explain query on that data, so just to kind of get the details of like planning the query, but not actually run the query, it would take 9.6 minutes. So like that's how long it took to plan the query, not run it. The scan would have taken like days because it would be scanning through a lot of data. Now watch what happens when we switch this over to an Iceberg table. Okay, this is actual data from like Netflix and their actual experience. Using an Iceberg table, the amount of splits that had to be scanned went down to 15,218. Okay, so you went from 400,000 per day of data to about 15,000 total. Okay, so the amount of data you're gonna have to be scanning has shrunk by a lot. Again, one way to speed things up is to scan less stuff. Okay, and to actually plan this, query, it only took 10 seconds. Because again, it goes through that path. It can again reduce, it doesn't have to open a bunch of files to figure it out. It just uses those manifest files and those manifest lists to narrow down the files without ever actually having to open them. So, you know, you may do some Parquet filter scanning later on, but oftentimes you don't need to because you've already eliminated that file when you're looking through that manifest and say, hey, I don't need to look at this file. And you're saving yourself a lot of time in the planning. Okay, so then total all in, it took 13 minutes to do the full query. Okay, so you went from almost 10 minutes just to plan the query to 13 minutes to actually do the job. Okay, can it get better? Maybe it can. Oh, wow, okay. Okay, what happens if we add minimum maximum filtering? So now we're not just narrowing down the files through partitioning, but now we're adding the fact that you're looking at the individual files, determining like what is their like value range, and saying, okay, this particular file doesn't have any values that would apply to my query, so let's not look at that file using min-max filtering. So that reduces the amount of splits down to 412 splits. Okay, now the planning took a little bit longer because it's doing a little bit more fine-grained pruning, but hey, the extra 15 seconds of planning saved you several minutes worth of execution. Okay, here you only had a 42-second wall time. Okay, so you can see like how Iceberg is dramatically just shifting the performance of the query. Okay, and it's doing it a lot through the planning, not by using more computing power, okay, not by increasing your cloud bill. Actually, it's saving you on your cloud bill because you're reducing the amount of processing power you need to execute queries at scale. Okay, so it's getting you access to the data and cutting costs. That's pretty cool. Now, the benefits of all this is that now you can officially make smaller updates, because now if I want to update like without one record, instead of having to identify the partition it's in and update the entire partition like in Hive, I can update that one file. Like we can just use those manifest lists and narrow down that one file that has the record I'm updating and just update that one file. So we can really quickly make those files because we're doing it at the file level. You have snapshot isolation, because again, we're basically what happens every time you do a transaction, you're creating a snapshot. And that's going to give us the ability to like move back and forth between snapshots. It also provides us those asset guarantees. So what happens if someone's writing data, they're writing a new snapshot. So they have nothing to do with the current snapshot. So if I'm a reader and I'm sending in a query, I don't have to worry about the person who's writing at the same time, because they're writing a snapshot that I'm not querying. I'm querying the current valid snapshot, which those files are never going to change. So I'm scanning those files, and I'm scanning the files as they were during that current snapshot. And that other person could be writing at the same time. Multiple people could be writing at the same time. And it's no concern to me as a reader. So it creates this real nice safety between multiple readers, multiple writers, multiple readers and writers. You have like safety, which goes a long way. Okay, you have concurrent writes. Okay, which again, you can have multiple writers. And the way that works is through optimistic concurrency. So essentially what happens is that if two writers are writing at the same time, and one completes and makes a new snapshot before the other, there's going to be like that moment of validation for the second write that checks like, hey, am I still in is the version I'm writing is a metadata file I'm writing, someone already beat me to that version number or that sequence number. And if they did, they're going to just update. They're going to go check to see if they need to rewrite the data again and then commit it. But you don't have to worry about like partially updated data or conflicting updates because they're going to be aware that this other write completed first, and they will act accordingly. So, you know, a lot of these kind of headaches that you had before now gone. And again, plus the better performance. Okay, because again, we're listing the files on the right side. So we're creating those lists of files that you'd be scanning through when you're writing files. Like all those files get generated then. Also, those files have column stats. So instead of you having to run these analyze queries periodically, you'll just always have sort of fresh stats that are in there in each snapshot that can then be gleaned off those snapshots, which means you're going to have reliable metrics on the data. Okay. Now we're abstracting the physical and you're exposing a logical view. So again, users don't need to worry about the individual files and how the table's structured. They can just treat the data as a table and think about it like they would any other table in a database or a data warehouse and interact with it and get the benefits of partitioning, min-max filtering, and so forth. So again, there's that hidden partitioning feature I talked about earlier, where you can specify a transform on your partitioning column. And that's not just by like hour, day, month, but there's other types of partitioning like bucketing, truncating, that really give you some really flexible options on how you partition. And again, the end user doesn't need to know how complex your partitioning is. They just run their queries, and if that query can benefit from the current partition scheme, it will. And that's basically, you no longer have to think about the physical, they can just focus on the logic of what they're trying to do. Compaction. This is more something like you're generally going to want to do. So what's going to happen is that since every time you write to the table, you're writing new files, what may happen, especially if you're like streaming in data, you might be generating a lot of small files. And the thing is that's going to slow down queries. Why? Because that means it's more files you have to open, then read, then close. So you'd rather actually have fewer, larger files. So in the APIs for Iceberg, they actually have utilities for running compaction jobs to take all those small files and turn them into bigger files. And you can also sort them at the same time. And just released in the last week in the newest version of Iceberg, they added Z order sorting. So you can actually sort it based on multiple fields and take advantage of like sort of that Z order curve approach. Okay, so you have that, which is really cool. Tables can change over time. You can pretty much update the schema any way you want. You want to update what the name of the table is, you want to drop a column, you want to add a column, you want to update the type of column, the data type of the column, reorder columns in a struct or properties in a struct. You can do that. Like it gives you total flexibility to update the structure of your table whenever you want, and you don't have to rewrite all your data. Like it's basically, it's up to sort of like the way the engine reads to then enforce a schema that's in those metadata files. And again, this is going to allow data engineers to experiment with the table layout. Like they can change the table without having to feel like, hey, I'm gonna have to go run like another 2-day writing job to rewrite this whole table again. And that allows you to kind of really discover what's the best ways to structure your data without having to be too scared of change, which again is going to also allow you just to have better data and be able to query that data faster when you're using this table format. Again, rich schema evolution support. So again, you can change the schema, you can change the partitioning. And at the end of the day, you don't have to worry about like syncing the table between multiple engines, because any engine, whether again, Spark, Dremio, so forth, that's going to access that data, they're always going to start by accessing the catalog. And the catalog, again, is always going to have that atomic pointer to the newest metadata file. So I make a change. So if I make a change in let's say, Spark, we run some sort of merge upsert job, and then I want to go read that data in Dremio, Dremio is going to pick up on those changes right away because they're going to be looking at that newest snapshot every time. And that really, really kind of allows the data to be consistent between different tools, and you're less worried about having like consistency issues. Now, if you want to learn more about Apache Iceberg, there's a lot of really cool stuff. And you can head over to iceberg.apache.org. You can see their blogs over at iceberg.apache.org/blogs. Over there on the Subsurface blog, we put out a lot of Iceberg content. So again, there's articles on the architecture, on hidden partitioning, on there's a article about table format comparison, where we actually compare Iceberg to Hoodie and Delta Lake and basically compare their features. All that you can find over there at dremio.com/subsurface. And then specifically, you go to the Apache Iceberg session, you'll see specifically all the Iceberg stuff filtered out. But there's a lot of also great content on Arrow and a lot of other great data lake topics. And if you want to get hands-on, you can just go to iceberg.apache.org, getting started, and then you can, get started with Iceberg. And again, you can also follow me on Twitter at @amdatalakehouse. You can also add me on LinkedIn. I'm constantly putting out stuff about Iceberg and data lakes and data lake houses. But right now, I'll open it up to questions. So I'll keep an eye out for questions for a moment, and we'll answer them. But again, yeah, definitely keep an eye out, because I definitely have a couple more pieces on table formats coming out, especially over the next month or so. Basically, lots of engines are available. So basically, I think you have like Presto, Trino, Snowflake, AWS Athena, Redshift, and you can also use Impala. I want to say there's one of what was the one that's kind of on the top of my head? In my table format article, I do have a full list, and it actually shows you that not only does it support it, but whether it has a read support, write support. Because the thing is, again, each of those engines that I just listed, each of them have to kind of develop specifically how they're going to support. So basically, they have to kind of write the code that's going to read those metadata files. And so each of them will have different levels of support, like whether they can just read the table, whether they can write to the table, and also just like differences in how they plan their queries and how sophisticated their query planning. And are they just taking advantage of the partitioning? Are they doing the min-max filtering? Are they doing extra things? Each engine will be a little bit different. Or adopt those techniques at different paces. But basically, most engines you can think of pretty much have some support for Iceberg, generally at minimum read, but probably a lot more than for most other table formats on the right side as well. Any other questions? I'm not too familiar with exactly how Iceberg works in Presto specifically. I think specifically in Presto, you can just read Iceberg tables. I think with Trino, I think you're able to read and write. But specifically, like what level of support they have for certain features, that I don't have. Like for example, like time travel, how is the query planning being done, things like that. I don't have specific answers to. The metadata should be automatic. Now, if basically it depends on the tool that's doing the writing, whether there's like they do extra stuff, because I think you can add like extra properties in the metadata, which some engines might do for their own like internal optimizations. But all that's done by the right now. If you write the table like Spark or Dremio, I know all that's done for you. Like I can't think of a situation where you would be editing the metadata file manually. Yes. So the question I just answered is generating the metadata fully automatic, or are there use cases where the user has to find the correct metadata files to edit them manually? So just to summarize my previous answer, generally you should never have to edit those metadata files manually. It should always be either done through an engine that you're doing the writes with, or using the Java or Python API that's also maintained by the Iceberg project. Is there an engine that focuses more on speed of read-write? I can only speak to where I'm from. So again, I come from Dremio, so I know that product really well, and I know of the speed optimizations of the Dremio product, and I can speak that it is very like optimized for speed, particularly because of open source technology, because you have Iceberg and the metadata that really allows it to prune files. You have Apache Arrow, which we're actually going to be doing a meetup soon on Apache Arrow, which allows it to have this in-memory format that allows it to process data faster, transport data faster, and then its own internal optimization, such as like the columnar cloud cache, which basically allows you to cache stuff when you're dealing with object storage quicker, and the really cool feature, which is reflections. What reflections do is they allow you to sort of materialize tables, but instead of like your traditional materializations where like people have to they have to query the materialized table directly, it creates like these automatically maintained materializations that can be used for queries on multiple views of the data on multiple data sets. So you get much more bang for your buck with them, and it's a pretty cool feature that can really take what took you maybe 30 minutes to query directly from your data lake and make it like a sub-second. But it's a mix of all that stuff. But so that I know, as far as like being speed oriented. But as far as other tools, I don't know. I'm not as acquainted with their intricate designs to be able to say one way or the other. Okay. Cool. Okay, I guess that is all the questions. Again, I'm constantly putting out more content on the table format data lakehouse space. So again, do follow me on Twitter at @amdatalakehouse. Do check out our articles over there at dremio.com/subsurface for all the subsurface content. So subsurface is the community that focuses on content around the data lakehouses in general. So basically how to kind of create that data warehouse functionality on the data lake. And far as like another question came in, are there any Iceberg competitors? Yes, there is. There's basically right now 3 table formats that are sort of vying for that sort of like, hey, we'll be the data lake house table format. So it's Apache Iceberg, which originated at Netflix, Apache Hoodie, which originated at Uber, and Delta Lake, which originated at Databricks. So those are sort of the main 3. I do have an article, which you can read over there at Subsurface, where I go compare all 3 of those side by side. And go over their relative feature sets, and I would say like with certain things like right now, some of the recent updates, they pretty much at parity with like things like schema evolution. Some of the things where like the biggest differences is like Iceberg uniquely has a feature like partition evolution, where the other ones, if you want to change your partitioning, you generally have to rewrite the table. So there's different features between the 3, and it also comes down to also engine support as another consideration that would go if you're comparing the 3. Like what engines do you use and what are the level of supports for these different formats? Those would be other considerations to take a look into, but those are the current sort of 3 formats that are out there. Cool. I guess with that, looks like there's no more questions. So I will wrap up. It's been delightful to spend this hour with you. Again, keep an eye out for more and more content. And I look forward to meeting with you all again sometime soon. And don't be a stranger. I'm always around.
Okay, thank you, everybody. Please join us again for Thursday Cassandra lunch and Mondays for data engineer class, same time.